All right, so this is 1.5. It's more on slope, which is what we covered in 1.4. So as usual, if y'all have any questions, raise your hand if I'm in the middle of a slide, or when I get done with the concept, just green check or red X if you understand or don't. All right, let's go ahead and move forward. So the first thing we encounter in 1.5 about slope is the slope of parallel and perpendicular lines. Now these first three statements about the slope of parallel lines are basically all saying the same thing in different ways. So if two non-vertical lines are parallel, then they have, let me get my pen, sorry. Make it a different color so it stands out from the black here. All right, then they have the same slope. So if you look at this picture down here on the screen, you notice that these lines appear to be parallel. Well, the only way that can happen is if they have the same slope. And I'm actually going to turn my video on real quick, but I'm going to turn it off because I want to show you something with my hands. Hopefully I'll come through okay. Just trying. All right. Very blurry. Let's see. All right. Sorry for all the blur and the glare behind me. Here's what I wanted to show you, and then I'll turn my video back off. So if you have, let's see if I can get this out from in front of the bright light there. So if you have two lines that are parallel, they have to have the same slope. If they have slightly different slopes, eventually they're going to intersect. So let me go ahead and kill the video. I'm in my hoodie trying to stay warm today. All right, so it should make sense then that the slopes of parallel lines have got to be the same, because that's the only way that they will not eventually cross each other. So statement 2 and 3 are basically saying the same thing. If two distinct non-vertical lines have the same slope, then they are parallel. If two distinct vertical lines, two distinct vertical lines, both with undefined, we learned that in the last section, undefined slopes, so the vertical line has undefined slopes, then they're parallel. In other words, all vertical lines are parallel, and we could also make the statement that all horizontal lines are parallel, as long as they're distinct lines. So moving forward with this material, looks like we lost Wes up there in Somerville. All right, so write the equation in point slope and slope-intercept form for the line parallel to this line right here through the point -3, 1. Okay, so there's a lot going on in this one problem. Your task is to start with, there's Wes, y minus y1 equals m times x minus x1. Once again, that's point slope form. And take it all the way down to write the equation of the line mx plus b. So you want the equation of the line that you're about to write to be parallel to this line. Well, the information that you gain from that is if the line whose equation you're trying to write is going to be parallel to that line, then it has to have the same slope. So the slope that you're going to use for this new line is going to be the same as your other line too. The point you're going to use, well, they tell you it goes through the point -3, 1. So that's the point you're going to use. So you're going to use this slope and this point, put it into point slope, and take it down to slope-intercept form. So that's exactly what I'm going to do. All right, let me get my black pen here. Y minus, well, y sub 1 is the given point, y coordinate, so that's just 1, equals m, which in this case is the same as the other line, so that's 2, times x minus x sub 1, which is negative 3. And now all I need to do is simplify and maneuver this to look like y equals mx plus b. So y minus 1 equals, I'm going to distribute that 2. This is actually x plus 3 there because it's minus a negative. So this is 2x, and then 2 times 3 is positive 6. Add 1 to both sides. Y equals 2x plus 7. Now let me tell you what you just found. You found the equation of the line that is parallel. Those two lines next to each other mean parallel to this line up here. Notice they've both got 2 as their slope, and it's running through the point negative 3, 1. In other words, if I plugged in negative 3, 1, I would get a true statement. So I'll just show you real quick. If I plug in the point negative 3, 1, 1 equals 2 times negative 3 is negative 6 plus 7, 1 equals 1. Check. So that's the equation of the line parallel to y equals 2x plus 1 through the point negative 3, 1. Y'all good so far on that? Dave says yes. Wes says yes. Michael doesn't say yet. Michael says yes. Okay, so you guys give this next one a try on your own for a couple minutes. So in this one, it's the same type of problem that we just did, just different point in equation. So you want to be parallel to this line going through that point right there. So see if you can work that out on your own real quick. And I will try to find you some equation writing music. Let's see. Oh, I need to get my computer worked on. I think I have too much crap on it. It's running like a Swiss car. Sorry, I'm trying to find y'all some equation writing music. I'll start working it here myself in just a second. Can't go wrong with King Crimson. My pen is acting funky today. Can't get it to right where I want it to for some reason today. Okay, so if you got y equals 3x plus 11, I do believe you're correct. Did any of y'all not get that and you're not quite sure why? I think everybody looks like they're, okay, Dave's typing, okay. Dave, that means you did get it and you're good. Okay, Wes is approving, he's clapping. Dave says, yep, he's good. And Michael says, I think Michael's trying to say something. He might be typing a book for us, which is fine. I just want to make sure I get any questions answered before I move on. Okay, y minus 5. Okay, that I started out with point slope form. Michael, that's y minus 5 equals 3 times x. That was minus negative 2. The negative 2 comes from here with the point. Let me delete all this so you can see the point there. The negative 2 comes from the x value in the point, and then it was minus a negative 2, so I turned it into plus positive. Does that help you understand? Okay, great. Excellent. I'm going to go ahead and move on, gentlemen. Okay, so slopes of perpendicular lines. If you look at the diagram here of perpendicular lines, you can see that whenever you have lines that are perpendicular, one is always going to have some positive slope, and the other has got to have a negative slope. The only time you're not going to have a positive and a negative slope with perpendicular lines is if you have a vertical and a horizontal line. And pardon the horizontal line there, it doesn't look very horizontal. But then you have undefined and zero slope. But other than that, the only way for two lines to be perpendicular is if one is positive and the other is negative. But there's a little bit more that we need to point out. So it's not just opposite signs. You also have that their slopes are reciprocals. This slope here is D over C, and this slope here is C over D. And actually, this is negative D over C. That is the opposite, meaning sign, reciprocal, which is flipped. So that is the characteristic that you're going to see occur with the slopes of perpendicular lines. So let's go through these three statements, which actually are all saying the same thing. If two non-vertical lines are perpendicular, then their slopes are opposite reciprocals. Once again, opposite is the sign, positive and negative. Reciprocal is flipped. Now, that's not the technical definition of reciprocal. The technical definition of reciprocal is that their product is -1. So I'll just give you a quick example. I'm sorry. Opposite reciprocal is that the product is -1. Definition of reciprocal itself is their product is 1. And I'll show you how that happens. 3/2 times 2/3. If I multiply straight across, I get 6/6, which is 1. That's the definition, and get a product of 1. So there are two conditions for perpendicular slopes. Opposite, that's the sign. Reciprocal, the flipped part. If the product of the slopes of two lines is -1, then the lines are perpendicular. That's where that says perpendicular. A horizontal line having a 0 slope is perpendicular to a vertical line having an undefined slope. So, our example here, find the slope of any line that is perpendicular to the line whose equation is this. And then we want to find the specific equation perpendicular and going through. So, there are a couple of steps in this problem. Because the equation of our original line is not written in slope-intercept form, we have to first get it in that form to figure out what the slope is, and then we need to figure out what the perpendicular slope is so we can start writing the equation of our other line. So I'm just going to start putting this equation here into slope-intercept form. I would add 12 to both sides and subtract x from both sides. When I do that, I get 3y is equal to -x plus 12, and then I need to divide 3 out of every term. Sorry, my pen keeps doing crazy things, maybe because it's so cold. Y equals -1. Sorry. Y equals -1/3 x plus 4. So my slope here is -1/3. Jesus, I don't know if I'm going to be able to stand this pen the whole time doing this. Okay, so slope here is -1/3, which means the perpendicular, okay, so that's just the sign for perpendicular slope, is positive, opposite sign, and flipped from 1/3 is 3, so it's just +3 for your perpendicular slope. This is the slope that you're going to use to write your new equation. And we're going to write our new equation by starting with point slope, y minus y1 equals m times x minus x1. And we're going to take it all the way down. Ugh. We're going to take it all the way down to slope-intercept form. Y equals m x plus b. All right. So I've got my slope that I need now. I've got my slope here, and I've got the point here that I'm trying to write the equation for. So I just plug those values in. Y minus -6 equals 3 times x minus -2. And then I'm just going to go back and change my minus negative to plus. Okay. And now I just work through the problem until it's in slope-intercept form. So y plus 6 equals, I need to distribute my 3x plus 6, subtract 6 from both sides. Y equals 3x, and there's an understood You won't see it, but there's an understood plus 0 on there, meaning that the y-intercept is the origin, the slope is 3. And this is the line, so this right here is perpendicular to x plus 3y minus 12 equals 0 through the point -2, -6. Y'all okay with that? Okay, sorry, I need to check my text message to make sure that's not the hubby not able to get up the hill. Okay. He literally lives 5 miles from, or we live 5 miles from where he works. He's been trying to get home since 2 o'clock. So, pardon me for checking my text messages. Not that y'all saw me do it, but I know y'all heard it. So, all right. Everybody good here? Okay, I see everybody's giving me a green check, and y'all are probably thinking, Libby, please move forward. We don't want to be here all day. All right. So, now we're going to move into talking about the average rate of change. If you're following along with the PDF notes, I skipped over a little bit of the notes because this is talking about the same thing, and I didn't want to waste your time today going over the same thing twice like that. Okay, if the average rate of change of a function, notice this picture here, and this picture is showing you height in inches in terms of the age of a male. So it would make sense that at 5 years old you're shorter than when you are 15 years old. However, notice that the trend starts kind of plateauing here, and actually it may even go down as you get older because some people become shorter as they get older. But the average rate of change of a curve is the change between any 2 points on the curve. So if we're focusing on this part of the curve, basically what our secant line is doing, and a secant line just passes through 2 points of a curve, so you can see that that passes through 2 points. The secant line is saying, well, we could kind of estimate what that height is going to be with this line here. Now, it's not a great estimation, but it's an estimation nonetheless. So what the slope of that secant line is representing is the rate that the curve is changing. So in this case, it's the rate at which the boy's height is changing. Not the actual amount of change itself, but how quickly his height is changing. So hopefully that is clear to you what we're even looking at. If not, raise your hand or give me a frowny face or something if this is kind of over your head. This can be a semi-difficult concept, but once you figure out what the procedure is, it's really not that bad. If the graph of a function is not a straight line, and I hesitate to use the phrase straight line because all lines are straight. If it's not straight, then it's a curve, but this came out of the book and it said straight line, so I put it there. The average rate of change between any 2 points is the slope of the line containing the 2 points. The line is called the secant line. So this point right here and this point right here are the 2 points on the curve that we're trying to figure out the average rate of change between. Okay, the man's average growth rate between the ages of 13 and 18 is the slope of the secant line. which is blank inches per year. Well, we figure that out by figuring out what the slope of the secant line is. Now at this point, all you know about the secant line are 2 points, 1357 and 1876. So I need to find the slope between those 2 points, or the slope of the line that goes through those 2 points. The slope of the line is given by y2 minus y1 over x2 minus x1. So I just need to decide which point am I going to call x1, y1, which one x2, y2. It doesn't matter, but I'll go ahead and call this one x1, y1, and this one x2, y2. So to figure out that slope, I just plug the numbers in. 76 minus 57 over 18 minus 13. Okay, so 76 minus 57, I don't have my calculator here, so I'm just going to do it by hand over here. That's 19 over 5. What this says is 19 inches every 5 years, but that's not what they wanted us to figure out. They wanted us to figure out inches per year, not per every 5 years. So what we need to do to answer this question specifically is do this division here, 19 divided by 5, and that will give us what happens every 1 year. So 19 divided by 5, let's see, 5 into 19 goes 3 times. 3 times 5 is 15. And I carry my 4 down there. 5 doesn't go into 4, so I need a decimal point. Carry it up, bring down a 0. 5 into 40 goes 8. So 3.8 over 1 answers our question here. This says 3.8 inches for every 1 year. Are y'all good with that? Dave says yes. And Michael says yes. Great. Okay. All right. So this is average rate of change of a function in general. And you notice off to the side here we have a picture of a curve. We've drawn some secant line, and there are many secant lines. There are infinitely many secant lines you could draw. I could find the average rate of change here. And the average rate of change there is going to be less than the average rate of change here, which is going to be less than the average rate of change here. So you can have many different secant lines on any given function. And what calculus teaches you to do is to average all of the secant lines, basically. So I won't get into that because I don't want to confuse the situation completely, but this is kind of the beginnings of calculus here. All right, so notice that the formula for average rate of change is just delta y over delta x. That is your slope formula there. So you have to have 2 points, 2 x's and 2 y's to figure any of these things out. Now if you look below, I've given you a function x squared, and I want you to find the average rate of change first between an x value of 0 and an x value of 1. Well, before you can do that, you've got to figure out what the y values are for that. So before you can put it into the slope function or formula, you have to find f of 0, and you have to find f of 1 to get your y value. F of 0, well, I just stick it into the function there. 0 squared is just 0. 1 squared is 1. So this tells me that I have the point 0, 0, and I have the point 1, 1. So I'm ready to put that into my slope formula. y2 minus y1 over x2 minus x1. So 1 minus 0 over 1 minus 0 is just 1 over 1, which is 1. And below here is a picture of that secant line at that point on the, or those 2 points on the curve. All right, so the next one asks me, okay, we'll find the average rate of change between x of 1 and an x of 2. So I need to do f of 1 to find out the y value there. 1 squared is 1. An f of 2, well, since I'm putting it into x squared, 2 squared is 4. So that gives me the points 1, 1 and 2, 4. Average rate of change, 4 minus 1 over 2 minus 1, which is 3 over 1, or just 3. An average rate of change is 3. And the last one, I do the same exact process. So the first thing I need to do is find f of negative 2. And let me point something out first before we finish this part of the problem off. Notice the average rate of change of this line here is 1, and that is less steep or changes less quickly, slower, I guess, than the average rate of change of that secant line. And notice that this is more positive than that one is. So it's steeper, it's changing quicker than the first one is. Okay, so let's continue with this last one. F of negative 2 squared is 4. And f of 0 is 0. So I have the points negative 2, 4, and it's a 4, and 0, 0. So my average rate of change is 0 minus 4 over 0 minus negative 2, which is really plus, negative 4 over positive 2 gives me an average rate of change of negative 2. And notice this is a negatively sloped line over here. So this is telling you how fast something's changing. So it should make sense that as you move to the outer edges of the curve here, that it's changing quicker than towards the center. Is that cool with y'all? Dave says yes. Michael says yes. Excellent. We've got one more slide to go. Okay, so a practical application of average rate of change is average velocity. The average velocity of an object is its change in position divided by its change in time between the starting and ending positions. If a function expresses an object's position in terms of time, the function's average rate of change describes the object's average velocity. So velocity is not just speed. Velocity is your change in your speed, how quickly your speed is changing. So if you're only driving the same speed the entire time you're on a trip, your change in that speed is actually 0. If you roll a ball downhill, at the very top of the hill, its speed is going to be changing slower than when it's towards the bottom of the hill. It's going to pick up speed, basically. So velocity is talking about your change in your position over your time, which is your speed. All right. Let us look at this. So notice your formula for this particular problem has your change in position, S is position, over your change in time. And we are given the formula here. S of t equals 4t squared, where t is time in seconds after the ball is released. And, oh, I'm sorry, yeah, position, distance in feet. S of t is your distance in feet. Okay, so find the ball's average velocity from. Well, the first one we want to do is a time of 1 second to a time of 1.01 second. So we're rolling this ball downhill. All right, so S of 1 is equal to 4 times 1 squared, and I'm just getting that function from right here. It was given to me. I've got to get my S of t value, because t is 1 here. I don't know what my y value or my S of t value is yet. So this is just 4 times 1, since 1 squared is 1, which is 4. That gives me the point. Every point in this problem is of the form t S of t. So my S of 1 is 4. That's the point 1, 4. All right, now I need to do 1.01. So S of 1.01 is 4 times 1.01 squared. Let me get my little calculator here. I'm not good at doing decimals in my head. I'm terrible at it, actually. I can't remember. I've got a newer phone, and I can't remember where the calculator is either, which is awesome. Let me see if I can find it in Tools. Hopefully it's there. Yes. Okay, so 1.01 squared is 1. I'm trying to figure out how to put a decimal point on here. I had it figured out at one time. There we go. 1.01 times 1.01. 1.01. And that equals 1.0201. So this is 4 times 1.0201. And that gives me 4.0804. So this is the point 1.01, 4.0804. Okay, so I've got my 2 points. That's what I'm going to use to find my change in S over my change in T. My S of T values are 4.0804 minus 4 over 1.01 minus 1. Okay, so 4.0804 minus 4 is 0.0804, and 1.01 minus 1 is 0.01. So what that says is this thing changes a distance, so this is in feet per second, changes 0.0804 feet for every 100th of a second, I can do the division and figure out how fast that is every 1 second. So that, let's see, 0.0804 divided by 0.01 gives us 8.04 feet per every 1 second. Okay, so that's at the beginning. That's at second 1 and at second 1.01 of letting a ball roll down a ramp. We already know what, okay, so for B here, it wants us to do the rate of change between 1 second and 1.5 seconds. Well, we already know that S of 1 is 4, so that's the 0.14. Now we need to do S of 1.5. So that's 4 times 1.5. Ah, that's terrible. Let me start over on trying to write that. Okay, so 1.5 squared, which is 4 times, okay, 1.5 times 1.5 is 2.25. And 2.25 times 4 is 9. So that's the point, 1.59. All right. Our average velocity between 1 second and 1.5 seconds, it should be faster than the velocity, or it should change more than the velocity between 1 and 1.01 seconds, because I'm moving further down the ramp at 1.5 seconds. So 9 minus 4 over 1.5 minus 1 is 5 over 0.5, and 5 divided by 0.5 is 10, which is 10 over 1, so that's 10 feet every second. So you can tell I'm starting to get faster and faster. Dave, I see you're typing something, so I'm going to hold off for a second. Not typing, okay, now you are. Okay, you were lagging. All right. So are both of y'all okay so far on A and B? Yep. Okay, so I'm going to let you try C by yourself and see if you end up with the same thing I do. So I'm going to turn on some music and give you a moment before I start doing it on the screen here. So see if you can figure out how fast the ball's speed is changing, so its average velocity between 1 and 2 seconds. And when you get a feet per second, try to type it in the chat window there. Did y'all get 12 feet per second? Don't just say yes. Definitely check my work. I do make mistakes. Okay, Dave says yes, he got 12 feet per second, and Michael says yes, 12 feet per second. So we have between 1 and 1 100th seconds a change or an average velocity of 8.04 feet per second. Between 1 second and 1.5 seconds, the average velocity was 10 feet per second. And between 1 and 2 seconds, it was 12 feet per second. So what does this tell you about how the ball rolls? You can type your answer in the chat window. Okay, I see that Dave is typing. Means it is increasing feet per second. Pretty much it means, if I were interpreting this, it means that the ball is getting faster and faster and faster as it rolls down the ramp, because I can see that it's changing more drastically the further the time goes. It rolls faster. Exactly, Michael. That's exactly. Okay, great, Dave. I'm glad you see that. Well, gentlemen, that brings us to the end of our lesson. So don't forget that 1-4, 1-5, and 1-6 homework quiz are due Monday, February 10th. That's not this coming Monday, but the following Monday at 11:59 p.m. Quiz will be open at 12 a.m. on the 6th of February. Next, oh, I forgot to change this. Sorry. Next lecture is not today. That's where we are. The next lecture is Monday, February the 3rd, day after Super Bowl, I guess, and it'll be over section 1.6. Hope to see you then. Thank you, gentlemen, for hanging in there. Stay warm and go play in the snow. Yes, I would agree, Dave. It is beer time, and I would say Miller time, but Miller is crappy beer. I will. Thank you, Michael. You do the same. If y'all are driving tonight, be extra special careful. If you don't have to get on the roads, don't go near them.